Hello and welcome to this Chapter 5 discussion on thermal chemistry. When we see the word thermal chemistry, probably the things that come to your mind are thermal would be heat, right? And chemistry is what we've been studying this entire semester. So when we see this word thermal chemistry, know that this involves both stoichiometry and heat exchange, okay? And in general, the stoichiometry is what's going to be kind of the overarching theme, and the heat exchange is what's specific to this chapter. So keep that in mind. But as we're going through this discussion, we're going to start with some of the theoretical applications of thermal chemistry. But first we have to start with some definitions and such. So let's go ahead and look at that. So energy, very basic definition for energy is the ability to do work or transfer heat. Okay, so work is an energy used to cause an object to move. And these are very physics based. So if you go to physics, take some physics class, you'll see these definitions being used. Heat is the energy used to cause the temperature of an object to rise. And so if you see something with a specific temperature, if that temperature increases, that means that some of that or that increase was due to heat actually being added to that object or that system or whatever that thing is we were viewing. So potential energy is one of the major types of energy that there is. There's potential energy and kinetic energy. And potential energy is the energy based on the position of an object. So this is a classic physics definition, energy based on position. But for chemists, another thing we have to bring into is the chemical composition. So the types of bonds that are in the molecule, those bonds actually have potential energy invested in them in order to actually create them. So, and then there's kinetic energy, which is an energy of motion. And so if an object's moving, it's got to have some energy that is essentially propelling it or pushing it. And so that's the energy of motion. So kinetic energy has a very nice equation. I just wanted to show this equation. We won't be using this on exams or anything, but just to show what the kinetic energy is. So Ke, this is one term, probably should have been a subscript E, but Ke is equal to 1/2 the mass of the object times its velocity squared. So the faster it's going, the higher the kinetic energy. The heavier the object, the higher the kinetic energy. The other one, the energy based on position, is very much just based on position. Okay, so if something has a higher position, a higher altitude, say up here, its energy or its potential energy is much higher than something that's at a lower altitude. So going back to these types of energy, heat and work, remember that heat energy that is transferred via heat is said to always be transferred from hot objects to cold objects. So heat can only be transferred in one direction. It depends on the relative temperature of the two different objects. Only heat can only be transferred for something that's at a higher temperature to something that's at a lower temperature. And so heat can only be transferred in that way. Energy is, of course, used to move an object over a distance, and it can be shown, well, it's derived this way, where the energy for a chemical system, this is generally how the work is applied. So if a chemical system at a constant pressure, so this is pressure right here, changes its volume, there's either work that's being done on that system or that work is doing or that system, excuse me, that system is doing some work. And so we'll be looking at both of those examples in the next few slides. Finally, we're talking about energy, and we've already discussed energy in the form of electromagnetic radiation, so photons having some energy, and we've looked at this particular unit for energy, the joule. One thing I want to point out for the joule is that if you break down the joule, which is a unit, right, into even simpler or more basic units, you see that a joule is actually equal to a kilogram meter squared per second squared. Okay, so that's the classic physics unit for energy, and it's SI unit, right? But a traditional unit in chemistry is that of the calorie, which is very much a heat-related energy unit. And that 1 calorie is about 4 joules. You see, it's exactly 4.184 joules. And so a joule is smaller than a calorie, or a calorie is larger than a joule. So those are a couple energy units to be aware of. One other thing that we want to point out is that these calories here are not the same as the nutritional calories you see on the back of packages. A nutritional calorie is actually a kilocalorie. So it's 1,000 of these calories, or 4.184 kilojoules. And so that is what you would see on the back here. So if a Snickers bar is 285 calories, you could actually calculate how many joules of energy is in a Snickers bar by doing a conversion from the nutritional calorie to the calorie unit that we use, and then over in doing a conversion from calorie into joules. And so you'd find out that it's 1.19 times 10 to the 6 joules is how much energy one Snickers bar has. So in addition to units, we need to also have some definitions so that when we're talking about things, we can actually have correct signs on our equations. So energy is transferred between a system and a surrounding. So energy has to go somewhere or come from somewhere. It can never just come out of nothingness, or at least it doesn't in our everyday experiences and in all scientific literature. Okay, so a system is the part of the universe. A couple of definitions. A system is part of the universe we're interested in studying. Most of the time for this class, that will be the chemical system. So we're talking about the chemicals actually interacting and doing some sort of reaction, and there'll be some energy exchange from those chemicals and the surroundings. Now, the surroundings are the rest of the universe, but we often limit that to very immediate surroundings. Like if it's done in water, the systems is the chemicals. If it's an aqueous reaction, the system is the chemicals in the water, the solutes, and then the solvent, the water itself, is the surroundings. So if we were to look at, this is actually a depiction of a car engine piston. So if we were to look at this particular depiction, our system here would be the chemicals or the gases in the piston, and then the surroundings would be the piston itself. And so if we were to do some sort of reaction, say form water in here, the system would be the water, or the reaction of the hydrogen and oxygen gas going to form water.